Well, as promised, today we are going to be discussing binary, the second number system that we're going to be using in this class. Let me which is base 2. Being base 2, it has only two symbols, 0 and 1. It is the most basic of number systems. Like base 10, though, it works a lot in the same way. For example, when you're counting, you have 0, you start from 0, then you add 1. You've run out of symbols to use, so you roll over to 0 again and carry the 1. So you go from 0, 1 to 1, 0. Add 1 again to make 3. And then you can add 1 again to get 4. Roll over to the 0 here. Carry the 1. 1 and 1 is 2, but you don't have 2, so you roll over a 0 again and add a 1 in the next column, the next digit. So these correspond to 0, 1, 2, 3, and 4. In base 10. So the value of each digit, each position, is going to be 2 to the increasing powers, like so, where each position in decimal is valued at powers of 10. Binary, it's to the power of 2. It's the power of the base that you're using. So the value of each position is going to be 1. 2 to the 0 is 1. 2, 4, 8, 16, 32, 64, etc. To get the value in decimal, you would, let me just throw out a random number here. You would, and this is in base 2, so you use the subscript 2. You would multiply the value of the symbol that you're using, in this case, just 1 or 0, times the value of that position. So 0 64s is going to be 0. 1 32, 32. 0 16s, 1 8, 0 4s, 1 2, and 1 1. and then you add them up together. And that gives you what, 43? I'm doing my basic math right? So that equals 43 base 10. One thing to notice with number systems is the smaller the base, the more digits you need to represent a number. In this case, you didn't, without using the first leading 0, you have 6 digits or 6 bits. Binary digits are called bits. 6 bits to represent a number that is only 2 digits in decimal. So while computers use binary, it is not space efficient as far as how much room it takes to store a number. When we get into hexadecimal, we'll get into a more efficient way to represent numbers. But for right now, we're just tackling binary. So you take the value of the position, multiply it by the value of the symbol that you're using, or that's there, and then you add those values up to get base 10 equivalent. Now to go the other direction, convert something from base 10 to base 2. That's don't have enough room here, so I'm going to erase some of this. Say you have a number 74. Okay. Easiest way to do this by hand would be to write out your powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256. Just get a good range there going. So 74 is between 64 and 128. So there's going to be a 64 in there. So you put a 1 in the 64's position. Let me put it over here. Then you subtract 64 from your number. Gives you 10. You started with 64s, so the next one up is 32. Is there any 32s in 10? No. So you put a 0 there. Is there any 16s in 10? Nope. Put another 0. There an 8? Yep. So you put a 1 there. And then subtract 8. Is there a 4? Nope. So put a 0 in the 4's position. There's a 2 in the 2. A 2 will go into 2. So put a 1 there. Subtract 2 again. And you get 0. So that is your last position, 0. So there's your number in binary. To me, that's the easiest way to do it. That's the method that I use most frequently to convert binary to decimal to binary. There's another way that's actually easier for computers to do, where you take the number and divide it by 2. And that gives you, what, 37? Right? Is that right? Yeah, 37. With a remainder of 0. So you put a 0 here. You put the remainder over here. All right? Let me remove that to avoid confusion. And then you divide that by 2. And you get, what, 18? 18 with a remainder of 1. And then that 1 goes into the next position. Then you divide by 2 again. Gives you 9 with a remainder of 0. Put a 0. Divide 9 by 2. And you get 4. Remainder of 1. Put a 1 there. Yes?
So this is basically just how many times you say that number?
No, you're dividing the quotient from the previous calculation by 2. Yeah. So you have in this case, 2 goes into 4. 2 goes into 4 2 times. The remainder of 0. Put another 0. 2 goes into 2 1 time with a remainder of 0. Put another 0. 2 goes into 1 0 times with a remainder of 1. So there's your, let me just make the distinction here. So you see we got the same result, just 2 different approaches. One starts from the left and works right. The other one starts from the right and works left. You can see how this might be easier to program in a computer to generate a string of 1s and 0s where you just do the mod of each successive, the modulus of each successive quotient of 2, mod 2 of each number to get the string, the digit that it goes into the next position, and you just concatenate to the left of this with the string. Now another way to, in the case of with computers, another way to represent a binary number, this would be 0, B, 1, 0, 0, 1, 0, 1, 0. This 0B at the beginning of it indicates that the following number is binary. This becomes important in later classes, in particular computer organization, where you learn assembly language, and some things are easier to represent in binary than decimal. So Yes.
version of base 10 to binary, do you have to add that zero in front of, or is it just implied version?
The 0 in front of what?
The binary. I know.
Oh, right here?
I'm saying, you know, we do any negative when they start with a 1, the binary.
Oh, up here?
I'm talking about when you convert it from base 10 to binary.
Okay.
Don't you have to have a 0 in front of those so that it's a positive number?
That's if we are using a 2's complement representation. Haven't quite got that to that point yet, but yes, you are right about that. But that's using 2's complement, and we'll get to that in just a minute. But those are the two ways of converting from decimal to binary. Now, we'll go ahead and handle 2's complement right now. We got, so far we've been talking about positive numbers. How do we represent negative numbers? Well, decimal, you just put a negative sign in front of it. That doesn't work with binary because computers don't recognize the negative sign in their circuitry. So, if you have a negative number, say negative 43, the way to represent this number as a negative uses what's called 2's complement. Why it's called that, I'm not exactly sure, but that's what it's called, and we'll keep using that. There's 2 steps to making it, well, 3 steps to making it a negative number in binary. First, convert the value, the magnitude of the number into binary. So you have a 32 in there, 32 x 11. You don't have a 16. You have an 8. 8. That's 3. No 4. A 2 and a 1. Okay, so that's 43 in base 2. Okay, so how I got that? All right, so how I got that? So this is in base 10. Now you convert it to a negative number. Now to do that, you have to use a even number of 8 bits, or even number of bytes in the representation. So here we have 6 bits. To make it a full byte, add 2 leading zeros. Okay? That doesn't change the value of it because they're just 0. So you now have 8 bits. Then to convert it to a negative, you flip all the bits. 1, 1, 0, 1, 0, 1, 0, 0. Okay? So You have the inverted bits. Then you add 1 to it. And that is your 2's complement. You invert and then add 1. You invert the bits and add 1. Yes.
So you added 2 zeros in front of it first.
Yes. To make it an even number of 8 bits. A multiple of 8.
Why did you do that?
Because most computers typically use groups of 8. Yeah. A 8-bit number can represent in 2's complement 127 to minus 128. Okay? So when you look at the number line, I'll just do 4 bits instead of 8. But you have 0, 0, 0 for 0, of course. Well, let's put that in the middle. 0, 0, 0, 0. Counting up, you have 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And these are okay. So you subtract 1 from that, from 0, what would you get? You roll everything over, like the odometer in your car. You go to 1, 1, 1, 1. You subtract 1 from 0 and you get 4 ones. Subtract 1 again. Oh, whoops. And you keep going until you get down to here. So this is 0, 1, 2, 3, 4, 5, 6, 7, minus 1, minus 2, and then minus 8. I believe. Yeah, that's right. That's right. So, yeah. But you notice, like you brought up, in this case, the leading digit, the most significant bit, the leftmost bit, is a 0 for positive numbers and a 1 for negative numbers. Yeah.
So if you kept adding 1 to the positive number, wouldn't it eventually have a 1?
That's why you limit it to how many bits you're talking about. In this situation, I was because of space and time, I only did 4 bits. In 8-bit, you would count up to 127, and then it would roll over to minus 128. Yeah, it rolls around like I said, like the odometer on your car. On an old car that's all digital now.
Not groups, but different ways of putting it, like four bits, or like 8 bits.
Or typically it's done by groups of 8. So 8, 16, 32, 24, that sort of thing. So most computers nowadays are 64-bit.
Oh, that's
Yeah, that's how wide the bus is, which you get into in computer organization. How wide the bus is for carrying numbers from point A to point B within the computer. Yes.
For asking them, it's just no time. Can you re-explain, like, even though you did the 74 one and the 64, like, I still don't understand how you got like 1, 0, 1. Like, I don't understand how you get into numbers. Like, I understand what you're doing, but I see that you're showing the word, but I don't understand how you're getting like 1 and then no thing sequence 0, and then like say another 0 or 1.
Okay. Yeah, I'll do it. Happy to do another example. Everybody got the number line? Okay. Let's see here. Oh yeah.
So say my number was 15.
Okay.
Would that go to 8 bits or?
Yeah, you'd go to 8 bits for that. You would use 8-bit 2's complement for that. So give me a number less than 100. 70? Okay. 70. 70 and base 10. Okay. To convert that to binary, the easiest way to do it by hand, in my opinion, is to have your powers of 2, the value of each position that in the bit field, the string of bits, and find the number between, find the power of 2, the largest power of 2 that you can subtract from your number. In this case, it's 64. So 64, subtract it from 70, and you get 6. And you put a 1 in the 64's position. Okay? Can you pull 32 from 6? No. So you put a 0 in the 32's position.
Oh, you just start going down the line?
Yep. 16s?
No, so 0.
So another 0. 8s? Another 0. 4? Yeah. So it's a 1. 2? Oh, you subtract the 4 from the 6. You get 2. You can get a 2 from that. So put a 1 in the 2's position. And that leaves you with 0. Is your last position. So that's your number in binary. Okay? Is that a little bit clearer now?
Yeah.
Okay. Now, with math, with binary, works the same way as decimal. So say you have 2 numbers, 1, 0, 1, 1, and 1, 0, 1. Okay? So you add just like you would in decimal. 1 plus 1 is 2, but you don't have a 2, so you put a 0 and a 1. Carry the 1. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. And then 1 and 1 is 0, carry the 1. Oh, it makes a nice even number. And to verify this, you would do, this is an 8, so 8 plus 2 plus 1 is 11, right? And 4 plus 1 is 5. 5 plus 11 is 16. And this 1 is in the 16th position, so you can check the math that way and verify that it is the right result. Okay, now we're going to try something a little bit different. This is where 2's complement becomes really handy. A subtraction is just adding a negative number, right? So say you want to subtract 32 from, let's make it something a little bit odd. 33 from 68. Okay, the result should be 35, right? In base 10. Okay, so we'll convert this to binary. You got a 64 in there. So 1 in the 64s. That leaves 4 left over, so there's no 16, no 32s, no 16s, no 8s. There's a 4, and no 2s and no 1s. Okay. With practice, you can do this in your head too. I'm just kind of moving things along here. 32 or 33. You have a 32, which is this position, and then a 1 and zeros for the rest of them. Right? So you're wanting to do subtract this number from this number. Now you could do the whole borrowing and subtracting thing and all that sort of stuff like you do in decimal. Or you can make these 2's complement numbers, 2's complement, and make this a negative number. So there's 7 bits, so that's, make it 8. So you're wanting to subtract these numbers, or this number from that number. Okay? So what you do is you move this over. So 0, 1, 0, 0, 0, 1, 0, 0. And then convert this to 2's complement, a 2's complement negative number. So you invert the bits, 1, 1, 0, 1, 1, 1, 1, 0. Then you add 1. Okay. So that's your, now this is your negative 33. And then take that up here So it's 1, 1, 0, and then 5 ones. 1, 1, 1, 1, 1. And then you add them because it's now a negative number. Okay? So you add 1 to 0 is 1. 1 and 0 is 1. 1 and 1 is 2, carry the 1. Or 0, carry the 1. 1 and 1 is 0, carry the 1. 0, carry the 1. 1 here. 0, carry the 1. 0, carry the 1. But now you have 9 bits. Turns out this one is just garbage. You can ignore it. In circuitry, when we get to the adders and subtractors, this bit here is thrown out. It doesn't go anywhere. It's just an artifact of binary subtraction. So we have the result here of 35. Let's see if this is 35 as the result here. Got 1, 2, no 4s, no 8s, no 16s, and a 32. So equals 35, base 10. Works out nice and neatly, doesn't it? Now, yeah.
So basically, you had a problem in base 10 and you converted all the numbers into binary.
Mm-hmm.
Did it and then converted it back into base 10.
Yeah, just to show that the numbers work.
Okay, why did you? So you converted. So you made the 33 using the twos. Like what's it called?
Two's complement, negative number. Yes.
Negative number.
Uh-huh.
You didn't do that with the. Oh, okay. So you just added a 0 for the 68.
Yes. Yeah, it's a positive number. Yeah, I added that 0, leading 0 to to a negative number in binary, and then added the negative number to the positive number up here, which is the equivalent of subtraction. So, and the result worked out. All right. Yeah, somebody said I don't? Okay, what you got? Where are you losing it?
I don't even know. I like to ask okay, I get how you convert and do the add 1, but when you started on the 68 and 33, I was confused.
Oh, okay. That's just a straight conversion from 68 in decimal to binary here. So that's just that converted. The 33 is right here, converted into binary here. Okay, so I converted it to binary with a minus sign, and then converted to eliminate the minus sign, I converted it to a negative number. This is the negative equivalent of the binary equivalent to minus 33. Because 68 minus 33 is equal to 68 plus negative 33, right?
What's, okay. You see how you get a, okay. What's the, that's in converting that second negative. Oh, converting that into a negative.
Yeah.
Yeah, so if you had, that's basically 68 plus negative 33.
You understand why I'm making it the second number a negative number? Adding a negative number is the same as subtracting that number, isn't it? It's basic algebra. So, like, this is the equivalent of doing 68 plus negative 33, right? Yeah. So this is equivalent, right? So we're doing the same thing, just in binary. You, instead of subtracting a positive number from a positive number, you're making the second number negative through the 2's complement process, and then adding them together. Is it becoming a little bit more clear? No? Yeah. 32? Oh, this is the 32's place. This is the 2's place, and this is the 1's place. So I was just converting 132 plus 2 plus 1 equals 35. This is the 32's place of binary. Converting it back to decimal. Okay? It's one of those things that you just you'll get to remember after doing this for a while. Let me expand this out a little bit. 0, 0, 1, 0, 0, 0, 1, 1. This is the 1's, 2's, 4's, 8's, 16's, 32's, 64's, and 128's. That's the position. Kind of like in decimal, this is the 1's position, this is the 10's position. In binary, the positions have different values. 2 is like I did on the first on the first board. This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, etc. You just kind of. I'm sorry. These? Oh, that's the result of the addition. Yeah, that's what I was just copying these numbers down here, spread out a little bit more so I could write the value of each position. Okay? Let's see here. Still seeing a look of confusion. We'll get you there. One thing that a lot of people do is overthink things. I'm not saying that's what you're doing. I don't know. But computers and electronics are fundamentally fairly simple. Well, digital electronics are fundamentally fairly simple. All it is 1s and 0s. Don't make it more complicated than it actually is. You know, the invert and add 1. Yeah, that's a little bit more complicated than representing a negative number in decimal, but it's a simple process that we will show later on how to do that in circuitry fairly easily. Yes.
Replace like mandatory or something?
For an 8-bit representation, yes.
So
Well,
why you added it on to complement negative?
the negative 33, yes. Yeah, I added the zeros. You typically deal with groups of 8 full bytes. Just as a review, you got 1 is a bit, 2 is a crumb, 4 is a nibble, and 8 is a byte. 16 is a word. So those are the different terms for each grouping. When we get into hexadecimal, we'll be dealing with nibbles primarily. But crumbs are hardly ever used as a term, but it is out there, so I put it on the board. But bit comes from abbreviated form of binary digit. Byte is a long bit, long I, byte. What's half of a byte? A nibble, if you're not thinking about computers. And what's half of a nibble but a crumb? So that's where the terms came from. But anyway, no need for real distractions there. But I'm trying. I want to get you clear on this. What is the stumbling block? So adding a negative number is the same as doing subtraction, right? Okay. So this is converting the magnitude of each of these numbers, 68 and 33, to binary. Okay? Then to convert it into this form, I make the 33 a negative number in binary using the 2's complement system, where you invert and add 1. Okay? That gives you negative 33, equivalent in binary. Then you take your magnitude of the first number, which is 68 over here, take the negative number from here, put it over here, and then add the 2 numbers together, disregarding the garbage at the end. And the result is this binary number here, which is the equivalent of 35 base 10. Another example? I'm sorry?
Yes.
Another example? Okay. We'll disregard these numbers. And yeah, the nice thing about an hour and a half long class is there's time for more examples. Okay, so go with 83 minus 28. Okay? So the result, these are base 10. The result should be, what is that, 5 and 5? So the result should be 55, not base 5, it's base 10. Base 10. So first, convert that to binary. So you got the 1, 2, 4, 8, 16, 32, 64, 128. Okay. 83. You can get a 64 out of it. And then 83 minus 64, oops. Minus 64 is 19. Right? Can't get a 32, so put a 0 there. You can get a 16 out of 19, so 16. Put a 1 in the 16th position. Can't get an 8. Can't get a 4, so 2 zeros there. Can get a 2 and a 1. So that is 83 in base 2 in binary. Okay? But this is only 7 bits. We're going to deal with a byte. Yes.
On the 0, if she got 16 out of it, why should it be 1?
There's a 1 in the 16 position. This is the 64s. This is the 32s. 16, 8, 4, 2, 1. Right? So we couldn't, when we subtracted 64, we couldn't get a 32, so we put a 0 there.
Are you going like a
Yes, yes. I subtracted 64. You subtract 64 right here. Try to subtract 32. Can't do it from the result. You can subtract 16. So you subtract 16, put a 1 in the 16th position. The result is 3. Try to take an 8 out. You can't, so there's no 8s. Try to take a 4 out. Can't do it, so you put a 0 in the 4's position. Take a 2 out. You can, so you put a 1 in the 2's position. And finally, you have a 1 in the 1's position. Okay? And similar with the magnitude of 28. 28, what can you pull out of that? You can't do a 32, so pull a 16 out. And that's leaves you 12. And a 1 in the 16's position. You can pull an 8 out, right? So 8 from 12 is 4. And you put a 1 in the 8's position. And you got a 4 left, so subtract 4. You have the 4 there. And then the result, and subtract that from there, and you get 0. And then the rest are zeros. Okay? The longest bit field we have here is only 7 bits, so we add leading zeros to make them 8. So 8, 6, 7, 8. So now you have a binary representation of the magnitudes of these two numbers. So you move this over 0, 1, 0, 1, 0, 0, 1, 1. And then this one, we're going to make it a negative number. Yeah.
So can we make it negative?
Invert the bits.
So when you do that, whatever the end result is, where we have the one in that spot, that's when you, if you say you had a one in the 64 spot, on one you add 64.
That's if you're converting it back to decimal. Yeah.
Okay.
Yeah. So, but to convert this number here to a negative number, use the 2's complement system. Okay, which is inverting the bits. Ones or zeros become ones. Ones become zeros. Zeros become ones. I'm sorry? 2's complement. Okay? So you invert, and then you add 1. So that's 1 and 1 is 2, 0, carry the 1. 1 and 1 is 0, carry the 1. 1, and then 0, 0, 1, 1, 1. So that is equivalent to minus 28 base 10. See how that worked? All right. And so we're going to take the negative 28 and add it to 83. So we do 1, 1, 1, 0, 0, 1, 0, 0. And then you add them. You get 1, 1, 1, right? Yeah, 0, 1, 1, 0, carry the 1, 0, carry the 1. But that's 9 bits, so you can throw this one out, and that is your result. Yeah, the extra 1 at the end on the left, when you do 2's complement addition, gets thrown out. This is the answer right here. Okay, now let's just make sure that this is right. This should be 55, right? The binary equivalent to 55, right? So that's 1s, 2s, 4s, 8s, 16s, and 32s. So that's 32 plus 16 plus 4 plus 2 plus 1 is 52, 55. Somebody had a hand up.
This is for
Yes. Yes. For tests and homework, I'm just going to stick with 8 bits. 16 bits gets kind of cumbersome.
So 16 separate columns.
Yes. Yeah, it would get kind of cumbersome and time consuming. But the principles are all the same. You just add more leading zeros at the beginning of the number to the left of the number. It never. I'm sorry. Nope. So I think we have some clarity here. The second did the second example help? Okay. Any other questions on that? All right. Now we're going to tackle multiplication. Just real quickly, we'll get into how multiplication is done in hardware later on in the semester, but I just want to show you how binary multiplication works the same as decimal multiplication. All right, let's see here. So, say you have 1, 0, 1, 1, and 1, 0, 1. And you want to multiply. How do you multiply in decimal? I'm sorry? Start with the bottom right factor, bottom factor right digit, and multiply the top factor by that value. Because the values are only 1 and 0, the calculations are pretty simple. So 1 times 1011 is 1011. Oops. Okay? That is what is called a partial product. Okay? Now you move to the second digit of the second product or factor. 0 times any number is going to be 0, so it's going to be 4 zeros. And you've shifted them one position. Okay, that's why this method is called the shift and add method. Yes?
You're not putting that 0 as a placeholder, you're just going to shift it.
Yeah, I'm using the zeros as a placeholder at this point. I mean, you could skip it, but
Like, you put like a 0 as a placeholder, but it is because zeros are part of it.
yeah, it's just shifted over one position. The position of the digit, the bit of the second factor.
Would it be wrong if I put a 0 right there?
No, it's yeah. You just it doesn't affect the addition later on. So, and then 1 times the third digit of the second factor times the first factor is 1011, and then add them together. 1 0 1 1 1 0. Carry the 1 1 1. Same as decimal, just fewer symbols. Now let's look at the decimal and make sure we did this came out right. So 1011 is 8 plus 2 plus 1 is 11. 4 plus 0 plus 1 is 5. So that's 55. And so we got 1 plus 2 plus 4 plus 0 plus 16 plus 32. So 16 plus 32 is 48, 52, 55. And it works out. So the method of multiplication is the same as decimal. It's just ones and zeros. Yeah.
You don't need like zero placeholder like you would like the fraction.
No, you don't need leading zeros. No. Generally speaking, the largest number that you're going to get from multiplication is going to be the same number of bits as the total of each factor. So there's 4 bits here, 3 bits here. Your answer is going to be less than 7 bits or less. If you have more than that, you did something wrong. But yeah, it's a multiplication. Same system you used in elementary school for multiplication. Just with ones and zeros instead of 2s, 3s, 4s, 5s, 6s, 7s, and 8s. The multiplication tables are much smaller in binary. But so multiplication is pretty straightforward. But I think we can wrap it up from there unless there's any more questions about multiplication. No? Okay. Have a good day.